the show must go on. Welcome back. Maybe I'll say the right number this time, Math 65, Calc 1. For anyone that's not watching or watching later. This is 1.6. It is on the continuity of trig functions. Trigonometric functions. So. Let's go. I'll start off with trigonometric functions are. Continuous on their natural domains. That makes sense. When you draw them, they're straight lines. Not straight lines, they're curves, but there you go with the pen. Some of them have asymptotes, like the cosecant, secant, shit like that. But where their domain is, they're continuous.
What about n?
What?
What about n? Numbers like that,
It's where its domain exists, it's continuous on it. This follows along the lines of like the stupid definition of continuous functions. Is where they're continuous is so long as they're continuous on their domains. Tangent has an infinite number of discontinuities, but it's continuous on its domain. Because none of those discontinuities or those asymptotes are in its domain. So like this leads to some fun shit, where we have trig functions with other things. We're gonna take a look at, this is what we're doing first. Limit as theta goes to 0 of sine theta over theta. No, Jacob, wakey wakey. So what we're gonna do, this is called the squeeze theorem. So we're gonna obtain limits by squeezing. It's called the squeeze theorem. Suppose that g of x is less than f of x, less than or equal to f of x, which is less than or equal to h of x. For all x in some open interval containing c. Except possibly at c itself.
why is that the exception?
Because we're gonna show that this has a limit, but we cannot plug in 0. 0 is not in its domain. That's why. So, because we're doing everything approaching it, but we're not really evaluating what's happening at it. We'll also suppose, does that make sense?
Yep.
Suppose that the limit as x approaches c of g of x equals the limit as x approaches c of h of x equals L, some number. Then by the squeeze theorem. The limit as x approaches c of f of x equals L as well. So just add a little bit more to that, see what the equations kind of thing. We have g of x. It's less than or equal to f of x. And I'm leaving spaces so I can write limits in front of them in a second. It's less than or equal to h of x. We already had that. That was part of the supposition in the beginning. Then we're gonna do the limit as x approaches c on all of them. I guess I didn't need the space right there. Don't need that space. We said that this one equals L. And we said that this one equals L. The limit of g of x and h of x both equal L. So the only way we can be both greater than or equal to a number and less than or equal to the same number is we have to actually just equal the number. That forces f of x to equal L as well, to make that a true statement. Does that make sense? That's why we call it the squeeze theorem, because the limit we're approaching. And both of them were like, the values are getting closer and closer and closer, and they eventually. These two values meet at L while you squeeze in at them. And you're forcing the value in. We're going to apply that here in a second when everyone looks like they're done writing.
Basically, you're putting the limit on the outside of what you're trying to solve, and then eventually it'll tell you what the answer is.
We don't put the limit on the outside of what we're trying to solve, we try to find functions that are both above and below. What we're trying to solve, that happen to have the same limit. That's a good question. Let's write that in words. So how do we use this? We have f of x. We find two functions. One less than or equal to f of x. And one greater than equal to f of x. And hope they have, we hope they have the same limit. Alright, so applying this to limit. Of theta equals 0 or going to 0. Sine theta over theta. So it kind of helps to see a little bit picture of what's going on here. So like if we use the unit circle. R equals 1. Then this line right here is got a length of sine theta. This part right here is cosine theta. And I'm not sure of the geometry behind why this is true. But they argue that this distance right here is tangent theta.
For tangent theta, that's what the distance from the x-axis to
Where it would intersect the ray made by theta. It's that vertical distance there. The idea is you can see that tangent theta is bigger than sine theta. And we can just take a look at for small theta. Like, let's say theta is 0.1. Tangent theta of 0.1. Tangent theta or tangent of 0.1 is 0.0017. And sine of 0.1. I might have gotten too small. Oh, I'm in degree mode. That's the fucking problem. Okay, let's try this again. Tangent of 0.1. There we go. Tangent of 0.1 is 0.1003. I knew that didn't look right. Sine of 0.1 is 0.0998. So for small theta, tangent theta is actually, it's a little bit larger than theta, isn't it? Which is also, theta is a little bit larger than sine theta. So we can see that from the numbers that we tried, for values close to zero. So what we're gonna do, this isn't what we wanted, we wanna somehow get something where we have sine theta over theta. So like, what I'm gonna do is I'm gonna start off is, like, I need this to have a sine theta above it. And it's kind of hard to get it above it unless we do like the reciprocal of it. But first I'm gonna multiply by 1 over sine theta. Let's multiply everything by 1 over sine theta here. We see for theta being above 0, this is fine, it's not changing the sign or anything, we can multiply by this. It's a positive number. So this was, tangent was sine over cosine. So if I multiply by sine, this one actually becomes 1 over cosine. It's less than or equal to theta over sine theta. And this is greater than or equal to 1. I said less than, they're both greater than. You guys with me? Now, flip it. When we flip it, it changes the signs. It flips the direction of the inequality. Now we're almost where we want. All we need left is do the limit as theta goes to 0. What's the left side? 1. What's the right side? 1. So we have found two things that. When we squeeze in on, this is both greater than or equal to 1 and less than or equal to 1. And the only way that's possible is if that equals 1. Just having that low. I need that bottom. Equals 1. You will use that in some homework problems. Memorize it for now, you will find an easier way. To do this, like find it, show it another way, much easier without this trick shit. But we need to learn about derivatives first. We're not there yet. It's called L'Hopital. Squeeze theorem works on anything. We're just applying it to trig function here. Squeeze theorem always works. In fact, when I assume you guys are gonna transfer. If you decide to take more math classes, like if you're a math major. There's a class called real analysis and stuff like that, and you use this squeeze theorem on a lot of shit in there. To show that something will go to 0 by showing it's increasing and getting closer to 0 from above and closer to 0 from below. You learn a lot. Real analysis is not a fun class. You have a lot of proofs to do, like proving addition works. 1 + 1 is 2. Like, we know that's how it's defined. But no, they do it. No, Jacob. I see him there. It's the slow, it's not the blink, it's just the slow collapse of the eyes. Blinks are quick. You can see when someone's getting ready to nod off. Alright, you guys ready for another fun one? This was interesting, wasn't it? Maybe fun isn't the right word, but it was interesting. It's on syllabus. I don't have it memorized what day it is. We are doing chapter 2 as well before we do a test. It's on syllabus. I don't remember the date. Next one we're gonna do is limit. As x goes to 0 of 1 minus cosine x over x. We want to show this equals 0.
Thursdays, September 17th.
September 17th, there you go. I believe we have a group practice test before then, and before that, I will give you a practice test like on Canvas where you can like practice it before you do the group thing. The idea is work on it alone, figure out what you can, then come in here, get together as groups. And compare thoughts and maybe learn a little something from each other. And hopefully that elevates everyone's grades. Because no matter how good you are, you have something to learn. And you'll learn it from people that you might think, there's no way that they could share something with me, I'm smarter than them. But you will, you'll learn. That's for the egotistical people. Alright, so that's what we want to prove. We're gonna start with 1 minus cosine x over x. And we're gonna multiply this by 1 plus cosine x. If we do that, we have on top, that's a minus b times a plus b. That's the difference of squares, a squared minus b squared, 1 minus cosine squared x. The bottom is x times 1 plus cosine x.
Multiply by its reciprocal.
I multiply. It's weird to say conjugate, because I don't know that I've ever used conjugate with the trig before, but it is effectively like the conjugate, yeah. The trig conjugate, that seems weird, I don't like that phrase. This is something you would never think of without being shown it. Well, someone had to have. Someone had to have. Is there anything we can do with this? The top is sine, isn't it? Sine squared x? That's a trig identity right there, that's sine squared x on top. This one's almost done. We see it as sine squared x, but we can break that shit up. We can make this limit as x approaches 0 of sine x over x. Times the limit as x approaches 0 of sine x over x times 1 plus cosine x. Nope, the x is in the other one. Just 1 plus cosine x. Sorry. Like, that's not gonna work. And we already showed this one with 1, right? That's what we did in the last proof. Do we have any problems plugging in 0 now? We don't. This is 0 over 1 plus 1. Which is 0. So 1 times 0 equals 0. This for me is the big leap. That statement is true, we can plug in 0, we're multiplying by 2 over 2, it's 1, it doesn't change the value. Coming up with that idea is rough. But once you've seen like the strategy, it might trigger your idea again. For the next example, and the final example for today. Make sure you have some room on your page. I'm grabbing a fresh page for the next problem. Does anyone need this page up longer? So let's evaluate the limit as x goes to 0. Sine of 3x. Cotangent of 5x. over x cotangent of 4x. Always worth a try, can I plug in 0? I don't immediately recall what cotangent of 0 is, but I know sine of 0 is 0. And this is 0 on bottom, so these are zeros themselves, 0 and 0. We can't just plug it in as is, and it's not set up to do the sine x over x thing yet either. So we can't just plug in 0. So what, like, let's start off with. Well, first off, who here likes cotangent? Does anyone?
Break it down simpler, right?
Right, we're gonna tell cotangent to fuck off, we're gonna break it down. So let's rewrite that cotangent part as what it really is. This is cosine of 5x over sine of 5x on top. And this is cosine of 4x over sine of 4x on bottom. Hopefully that's something you might be inclined to try right away too. That's not a big leap yet. So we didn't like cotangent, so we told them to fuck off. Do we like fractions and fractions, complex fractions? No, we're gonna tell complex fractions to fuck off too. So like, let's get rid of the complex fraction on the bottom. Let's multiply this by sine of 4x over cosine of 4x. That'll get rid of the complex fraction on the bottom. But if we do it on the bottom, we have to do it on the top also. Which is good. Gets rid of that. Gets rid of that. Leaves behind ones. I'm gonna group together the things that have this. Those will go together, those will go together, those will go together. We're gonna say this is the limit as x goes to 0. We've got sine of 3x over x. And then without like having to do this over 2 lines, I could write the cosine 5x over sine 5x. And sine 4x over cosine 4x, or I can right away immediately just apply the limit to those individually as well. So let's do that. Actually, let's put the cosines together. Let's change this. Let's put the cosines together. Let's see, I'm gonna have a problem if I do that. I don't wanna do this. Let's put the cosines together. We're gonna have cosine of 5x over cosine of 4x. This is not an intuitive step. And then we'll have sine of 4x over sine of 5x. Okay, is there a problem with doing this one right now? Can I just do it and get it out of the screen? Off the page. What is that limit right there?
What goes into this?
Cosine of 5x over cosine of 4x, if I evaluated x going to 0, what happens? Cosine of 0 over cosine of 0 is 1, right? This is just 1. We're done with that bad boy. Alright, we are pretty close to, and I'm gonna write up here in a box. On that left one, remember, we defined it as limit as theta goes to 0, well, not defined, we showed. Sine of theta over theta equaled 1. But if I say theta equals 3x. To be the same what's inside here, I don't have theta down on the bottom yet, do I? But I can get it if I multiply the top and bottom by 3. So if I multiply this by 3 on top and bottom, now this is theta. And I can effectively, it's a constant multiplier, I can put 3 up front. So this first one becomes 3 times the limit as x goes to 0. And now that I've said theta equals 3x, this is sine theta. Sine theta over theta. We know this is a 1. This is going to be 3 times 1.
So you pulled the 3 out of the 3x, is that where you got that, and you put it in front of the sign?
Yeah, I pulled the 3. No, I didn't pull it out of 3x, I multiplied by 3 over 3. Which is multiplying by 1.
Okay.
I put the 3 on the bottom with the x. That way this matched this. So it's like doing like a U sub, I said theta sub. I did a theta sub there. And when x equals 0. Theta equals 0 on my sub, so I have that there.
Is there, I don't think I can think of it, but is there a way that won't work? To where you can do a theta sub? Is there a way that won't work? Because I'm just thinking if there's like any way you can get 0 at the bottom, that won't work at all.
Well, we have a 0 on bottom. If we plug in 0, this is 0. The key is we were trying to get it into the form of something that when we do the limit isn't 0. So this was already 0 over 0. It had a problem. I don't know how to answer that question. Like it already had the 0, so like the. We're trying to make it look like that and we made it look like that. So now we can avoid the 0 in the bottom isn't a problem anymore because we have a formula for that. That we showed in the last problem, or problem 2 problems ago. The question is, what do we do with this motherfucker? It's 0 on top, 0 on bottom. Well, what we kind of want to do is we want to take like a similar approach here. Which means like, I'm gonna split that bad boy up. We already showed this first part is 3. And that was 1, so this is really, at this point, we're at 3 times that limit. And what I'm gonna do to make this a little easier to see is I'm gonna write this as sine of 4x over 1 times 1 over sine of 5x. If we can make this shit look like this shit, we're good to go. So I can make this one look like that if I multiply by 4x on bottom. And this one would look like that, but upside down, if I had a 5x here. But I need to do it on top and bottom, right? I can't just willy-nilly multiply. I've already multiplied the top and bottom both by an x. I clearly need to multiply the bottom by another 5 to deal with that 5. I need to multiply the top by another 4 to get rid of that 4. So the motivation here was to do something that dealt with the sine of 5x and the sine of 4x. We put them on top and bottom, and then we said, what else do we need to do so that we didn't multiply by something that wasn't 1? We effectively multiplied by 20x over 20x. That's what we did. I just split it up. If I said multiply by 20x over 20x, you'd be like, nope, I'm not buying that shit. Hopefully you can see the motivation for doing it the way I did it. The same thing we did here with getting the 3x to match the 3x here, I wanted to do it here, but I didn't even have the x this time. So I got the x in there. I'm gonna pull a 4/5 out here. And we've got 3 times 4/5 is 12/5. Limit as x approaches 0 of sine of 4x over 4x times the limit as x approaches 0 5x over sine of 5x.
The 4x, did you multiply? Oh, wait, I see it. Never mind.
Did everyone with me on that? There was a lot going on there.
Yeah, no, I get it.
So we put the 4x on bottom and the 5x on top to deal with the sine of 5x and 4x. But we can't just do it for free. We have to make sure we're multiplying by 1. So like effectively everything would cancel, that cancels that, this cancels that, and x cancels that. Alright, so we showed this as 1. So now we're at this, just this remains. And it's upside down on what we want. So we can use the reciprocal. I'll do it on top and bottom. If I flip it, I've got a limit as x approaches 0 of 1 on top. Limit as x approaches 0 of sine of 5x over 5x on bottom. This equals that. That's probably something you're not used to doing. But let's do it where it's a little bit simpler, where you'll see it. 2 equals 1 over 1/2. If I multiply, to show this is true, if I multiply this by 2 over 2. This cancels and I just get 2 equals 2. So instead of having a number, you can divide by its reciprocal. That's what I did here. I had this, instead I divided by its reciprocal. Notice it's flipped. This here was 1. By that again. So this all boils down to 12/5, which is 2.4. Told you that's gonna take a lot of space. Now I'm writing big so that's legible to everyone in the room, but it's even on paper, and regular hand size writing, it takes up a lot of space. There is a lot to unpack there, I agree. Is there any questions on it? Because that's the last example we have for the section. If you're done and you understood everything, you're free to go, get the fuck out. But if you've got questions, we still got time to ask.
So, not about what we just did, but what we did to multiplying the 20x over 20x. Do you mean doing that to the sine 4x over sine 5x?
Well, this 20x over 20x is 5x times 4.
Or is that?
I was just,
example?
I was just saying what I effectively multiply by if I made it one thing. Here I split it up and divvied it up, but if I had just said multiply by 20x over 20x. There doesn't seem to be any motivation for it, it just seems like something I randomly did. I just wanted to make sure it was clear I was multiplying by one. So like, if there's a problem or two in there that's something like this. Try to take advantage of this one. And the other one you wanted to, wanna try to take advantage of was. Limit as theta goes to 0 of 1 minus cosine theta. Over theta is 0. I think you're what? I can't make it fill the screen any better.
That's good.
Those two are useful for now, when you learn, it's called L'Hopital's rule. Some French guy. You need to know derivatives first, it makes all this shit easier. And then you don't need to memorize this anymore, in fact. When I first started teaching, and I hadn't taught top one yet, I was in the math lab and someone walked up to me and I was like, how do I show sine x over x equals 1? As x goes to 0, I'm like. You don't have L'Hopital yet, I have no fucking idea, I completely forgot. This rule, this property, but we kind of need it until you learn other ways to do it.
Will we learn other ways to do it before the first exam?
No,
Okay.
you just kind of need to memorize that one.
That's it.
So you're telling me that big ass equation equals 2.4?
What?
You're telling me that big ass equation equals 2.4?
Yeah,
See, and this is why math sucks sometimes. You got big ass scary equations, and then you got 2.4 as your answer.
I think it's nice that it was something simple.
Well, no, I like that it's something easy and simple to answer, but it's like you start up there and then you show, if you were to show someone that you can have that and it equals that, no one's gonna believe you. And then you show them all the work in between, and eventually starts to click.
Right.
It's just crazy.
Alright, how the fuck do you say your name?
Olive,
Oliver.
we say Olive, but it's a little different.
Nice to meet you. I wasn't sure what gender you were, I'm like, I don't know. Gonna be calling on a girl's name or a guy's name,
Thank you.
yeah, welcome.
See ya.
Oh, you went with, I thought you were gonna take the trig one. Paula,
Sorry,
I thought you were gonna take the trig class.
no, why'd you do that?
Were you emailing, weren't you in both trig and,
I was in California, yeah, pre-calc.
yeah, pre-calc B was trig though. So you were in pre-calc B and this, I thought you said you were gonna choose the pre-calc B,
I was in pre-calc B and calc 1.
which is this class.
Yeah, we dropped the calc. And
One,
then-
and then you changed your mind.
No, this is this, are you talking about this? This is for computer science. Computer science.
Oh.
We're straight, alright. Thank you.
See you on Saturday.
Yeah. What's your name?
Friday?
Yeah.
Brilliant. Hopefully you'll be seeing that face a lot.
But if you're coming, I wanna know your name, like,
Hopefully.
it's hard to remember everyone's name, but the more people talk, the easier it is to remember. I will see you Saturday.
See ya.